them on Edmodo if you need them for reference.
Recently? When did we do that?
Yeah, about last period. Okay, so first thing we did, just like in the warm-up, sketch the situation. Right? Then draw a free body diagram. That's what we did next. And then we used the free body diagram to analyze the centripetal force, right? We noticed these two were both pointing toward the center, so those were our centripetal forces. Notice that your centripetal force, it's not a separate force.
Wait, mv squared over r is 1 revolution?
That's centripetal force. Okay. But what I'm saying is, when you analyze your free body diagram, your centripetal force may be a combination of forces. Or like gravitation, it could be just one force. Or it could be just a component of a force that you have. You guys remember the rubber stopper lab? The string was at an angle. The tension in the string was at an angle. Only the component that pointed in toward the center of the circle was actually the centripetal force. The vertical component of that tension was just balancing out the force of gravity. All right, anyway, then you're going to want to apply Newton's second law. We did that, right? We said that the sum of the forces with mass times acceleration. And sometimes you'll have to substitute v squared over r for centripetal acceleration. Sometimes you'll even have to take a step further and say v is 2 pi r over t, where t is the period. All right. For gravitation, these are your general principles. Gravity is the centripetal force. Right? We do all that other stuff that we talked about, and we'll find that gravity is directly proportional to both of the masses. So if a mass goes up, more gravity. If it doubles, you've got double the gravity. But it's inversely proportional to the square of the distance between the centers of the objects. So right now, Coco and I have a certain amount of gravitational attraction between the two of us. But if I leap over this desk and I stand by Mindy, and I cut our distance in half, there will be 4 times more gravitational attraction between the two of us, because we're twice as close. Right. It's based on the square of the distance. Yeah. The force of gravity is based on the square of the distance. So if you make your distance go up by a factor of 10, since the distance went up, the force goes down.
10 times.
And not by just 10 times, but by 10 squared times.
There's 100 times.
100 times smaller. Okay? If you triple the distance, it goes down by 9 times, 10 squared times. All right, but the opposite happens, right? If you get closer, the force is stronger. So if you take the distance and you cut it in half, the force has got to go up, but not by a factor of 2, by a factor of 2 squared. It goes up by 4 times. If you cut the distance by 5, right? And you started out at 5 meters apart, now you're only 1 meter apart. The force is stronger by a factor of 5 squared.
So it would be 25.
25 times greater. All right. Lastly,
They'll be on the upper end, right? Like this will be on the upper end, right?
everything.
Oh, okay, I get that, but like on the upper end specifically, I mean, like this.
Yeah, it's all there, everywhere. On your formula sheet, by the way, on the practice problems, you ran into a lot of. They were talking about density.
Yeah.
Don't. On the formula sheet, there's 2 things taking place here. First of all, rho is your density. It is how compact everything is. It's the mass per volume. Typically, we're talking about the volume of the sphere. We're talking about planets or moons or whatever. The thing to recognize there is that the volume is directly proportional to the cube of the radius. So if you double your radius, you haven't doubled your volume. Your volume's gone up by 2 cubed. It's gone up by 8 times. For the same density, then, you would have 8 times more mass. Yeah.
Oh, I wasn't here Friday. Did I miss anything?
Yeah, you missed a practice test. By the way, the practice test, guys, I have passed. I have posted on Edmodo with answers that are on the last page of the practice test. So if you want to check your answers, they're there.
We only get under an E, so well.
Okay. Lastly, yeah,
This relates to the density. So for question 22.
we're going to go over that together in just a minute. Sorry to cut you off. I did want to also mention on uniform circular motion, in general, you keep these ideas in mind, that the velocities are always tangent to the path, that the net force and the acceleration are always radially inward toward the center of the path. The forces cause the accelerations, right? Lastly, the sensation of being pushed towards the outside of the circle is just your own inertia. There's no force pushing you to the outside of the circle. You want to keep on going this way, but there is something pulling you in towards the center. Okay. So what happens if that yo-yo suddenly, the string right here got cut as it was moving in this direction? Where would it go? If the string gets cut, it's going to continue moving along this path. Okay. Of course, if gravity would come in, it would eventually go like that. But the instant it gets cut, it goes off in the direction of its tangential velocity. Okay. Let's look at number 20. If there's nothing pulling it toward the center, it's going to go straight.
Those are all the big terms we should know.
Any big terms?
Yeah, like those are only 3 big terms you guys remember.
Yeah, I think just centripetal acceleration is or centripetal force is enough as far as vocab.
All right.
All right. So Noam asked me about number 22 online, and I don't work on Sundays, so I didn't respond, but I did just post a response to you yesterday, this morning. Okay. On number 22.
Yeah, I didn't understand how to use that.
What is?
I'm pretty sure it's a.
So here's our-
22. Never mind.
And here's the new planet. From Friday's work. So the density over here is 1/3 of the Earth's density. And the radius here is 2 Earth radii. Okay. So all right, guys. Hey, excuse me. We don't have much time. So let's not focus on the scratches. Let's focus on our work. Totally agree. 100%. So we've got G here on Earth. We want to know how many G's we have on the planet. First off, because this planet is twice as large, a person on the surface of this planet, just based on distance to the center, how is the force of gravity going to compare? It'll be a force, right? When you double the distance, you take down the force and the acceleration due to gravity by a factor of 4. Oops.
If you look at that, you can't do
What
that.
was
You
that?
be like, ooh, like, I'm gonna take this away and then don't move.
Because it was a mistake. That's why I took it away. So, due to distance, right? There's only two factors, distance and mass. This planet is going to have a fourth of the amount of G's that you have over here. We okay with that?
So that's how you write it when you're writing it in the fraction. So the fourth on top, does that mean like the whole number 4 when it's on top?
Yeah. So it'll be 4 times greater. Yeah.
So if it's like 4 times greater, it'd be 16.
Yeah.
Like the problem before that didn't have that as a moment.
Okay.
We can look at that. Same thing.
Well, we can look at that too. But remember, there are two factors that we can both come into play. So we said that because of the distance, the force of gravity and the acceleration due to gravity would be a fourth. But mass also is a factor, right? So the person's mass doesn't change. The planet's mass did, right? And we know that it is a third less dense. Okay. Let's figure out how much more volume there is. Your volume is based on the cube of the radius. I think we just discussed this. If we double the radius, what happens to the volume?
It goes down by 2.
Goes up by 2 cubed times. So 2 times 2 times 2 goes up by 8 times. So this guy over here has 8 times the volume of Earth. Okay? But it has 1/3 of the density of Earth. So, compared to the mass of Earth, it has 8/3 the mass. Okay? So the definition again of density is mass times volume. I'm sorry, mass divided by volume. I did it again. And so if I wanted to know how the mass has changed, I would multiply density times volume, yeah.
So, density, there's no need to
No, we don't have to actually substitute in here. So I found the new planet actually has, even though it's bigger, anyway, it's got 8/3 of the mass. The mass is 8/3 bigger, but due to the distance, the force would be 4 times smaller. Let's put those two together. Yeah, multiply that by 8/3. 8/3 bigger due to the mass, 1/4 due to the distance would give you a total of 2/3 of G. And G is 9.8 on Earth, so it would be about 6.5.
That's not an option. This is 2/3. There's B. You have to
Oh.
That's the answer I think.
Oh,
2/3 of
that's
9.8.
what, okay.
Ethan asked about 21, which was very similar. 4 times the radius of Earth. What would that do to the force? Being 4 times bigger. It'd be a 16th, right? It would go down by 4 squared.
Wait, so what was
That's not an
that?
option.
Yeah, that's not an option. So what
That's
was
what
that?
I thought. It's not.
That's don't let me finish. So due to distance, it was a 16th of it, right? But it must have more mass because it's 4 times bigger and it has the same density, right? 4 times the radius would give you 64 times the volume. At the same density, that would be 64 times the mass. So because of the mass, it's 64 times greater. Because of the distance, it's 16 times smaller. 64 over 16 is 4.
Absolutely, yeah.
So it should be
That was
4G.
hard. Easy.
Okay. All right. Let's look at this open-ended question that you guys got on the way in with the car. Because it's going to draw from a couple of different units on this. And that's what they love to do on your open-ended questions. The back of the page that you got on the way in. Back of the page? Yeah, with the car going around the circle. So we can look at this guy right here.
Okay.
Do part A real quick. Draw a free body diagram. That car is going around the circle.